Hello everyone, and welcome to the fifth lecture of Electronics 1. Today I'm going to step back a little bit and look at some circuit analysis just as a review, because we're going to use it quite extensively going forward in this class. So as we've done even just recently with our amplifier models, we've used the voltage divider to calculate the voltage at a point between a pair of resistors. So like these resistors R1 and R2, we apply a voltage to the top of those resistors, V1. What will the voltage be, Vx? And just a clarification for those of you that are uncomfortable with a circuit drawn in this way. This is the exact same circuit, the top one just being shown in a shorthand format. Okay, so these are the same circuits. Okay, but let's talk about using the voltage divider to calculate the voltage at Vx. We all know at this point that we can calculate the voltage at Vx by taking the voltage V1 multiplied by the resistor that voltage Vx appears across, R2, divided by the sum of the resistors that are in series in the voltage divider. Okay, so straightforward enough. Let's extend that voltage divider to a pair of resistors that doesn't have ground at one end, but has a voltage source applied to both ends. Okay, so now instead of having ground on the bottom, I have V2 on the bottom, and again let's assume these resistors are R1 and R2, and we want to know the voltage at Vx. Okay, since this is a linear circuit, we can apply superposition to calculate the voltage at Vx that results due to each of the sources V1 and V2 individually, and then add the results. So if I first look at the voltage at Vx due to V1, so I'm considering V2 to be shorted here. So the point V2, if it was shorted, would be simply connected to ground. Then the voltage Vx1, so the voltage at Vx due to source 1 would be V1 times R2 over R1 plus R2, exactly like the first example we looked at. But now finding the voltage at Vx due to V2, now assuming V1 is shorted, and basically in my diagram, V1, the point that's labeled V1, would be simply connected to ground. Now I can calculate the voltage at Vx due to that source V2 as V2 times R1 now, because the voltage is appearing across R1, divided by R1 plus R2. Okay, summing these results together, I can get the total voltage at Vx is equal to V1 times R2 over R1 plus R2 plus V2 times R1 over R1 plus R2. Okay, so fairly straightforward to do, but you'll find it quite valuable to simply remember this equation rather than having to apply superposition every time you have a pair of series resistors with voltages at each end and you want to calculate the voltage at that midpoint. That's something that we're going to run into multiple occasions going forward, and particularly when we're looking at op amps here soon. To use this, so just a thing to remind ourselves of, to use the simple voltage divider equation, even like the first version of it that we used. It's important that no current leaves the junction of the two resistors. And I'll draw a diagram here to make it clear what I mean here in a second. Okay, so just going back to our simple voltage divider again, with voltage source applied to one end, ground on the other, R1 and R2, and Vx in the middle. My assumption here, in order to be able to calculate Vx in this way, this is only true if this current Ix is equal to 0. Okay, so this is the above equation here is only true if Ix equals 0. Okay, if Ix isn't equal to 0, okay, so in the case, let's say Ix is equal to something, it means that there must be some additional resistance or additional load that's out here that's resulting in this current flow, and that changes the voltage divider. The voltage Vx is no longer just appearing across Rx, it's appearing across Rx in parallel with some additional resistance. Okay, so again, we have to be sure that there's no current flowing out of that midpoint in order to apply these voltage divider equations, whether it's the simple voltage divider from a single source or the voltage divider equation here from a pair of resistors with voltages at each end. Okay, what happens if there is current flowing from that midpoint between the resistors? Oops. So if current does flow, then we have to use another circuit analysis technique that you should be familiar with, which is Thevenin's theorem. And this is going to come up specifically when we are dealing with transistor circuits and the bias network for transistors. So let's show and I'll show my resistors connected to a source like this now, just to be a little bit more clear maybe. Okay, and I have my voltage source V1, and I again have R1 and R2. So far this is no different, and I want to know the voltage Vx here, but now I have some current flowing Ix that's not 0. Okay, so again, this is should be review, but to apply Thevenin's theorem, step 1 is we replace V1 with a short circuit. Okay, so in this example we would short this out, and then step 2, we determine the Thevenin resistance. So that's the resistance looking back from the point where we're trying to calculate the source voltage. So what's the resistance looking back from this point? So our Thevenin, in this case, if the voltage source is shorted, then we just simply have R1 in parallel with R2. Okay. Step 3. We determine the Thevenin voltage. Okay. The Thevenin voltage is calculated by calculating the voltage at this point Vx, assuming Ix is 0. So we assume Ix equals to 0, and then find Vx. So we're going to call this V Thevenin, and that's again simple voltage divider rule that we started this lecture looking at. Okay, we use this Thevenin voltage and Thevenin resistance to draw an equivalent circuit. And that equivalent circuit is that Thevenin voltage in series with a Thevenin resistance. Okay, so this is V Thevenin, this is R Thevenin, and now we can replace that circuit that we started with this Thevenin equivalent circuit, and we can use it to calculate Vx, and if we know Ix. Okay, so that leads us to step 5, okay, which is to calculate Vx. Okay, so Vx here would be the Thevenin voltage minus whatever drop there is across this resistor, right? This drop across R Thevenin, which is going to be Ix times R Thevenin. Okay, so minus that Ix R Thevenin drop, and that allows us to calculate Vx. Okay, so we'll end this lecture here. It's purely for a review of some circuit analysis techniques that we will be relying on you to know going forward. So next class we'll dig into looking at some op-amp theory and presenting op-amps.